So in this section, we're looking at 10.5, absolute convergence, and the ratio and root test. We start off with two examples of some series, and we're looking at whether or not they converge. So for this series on the top, we have n starting at 0. When n is 0, we get 1 times 5. So we end up with 5. And then for our second term, when n is 1, we would have 5 times negative 1/4 to the first. So that would be negative 5/4. When n is 2, negative 1/4 squared will be 1/16. So plus 5/16. Okay, then we have minus 5/64. And this will continue like this. Now, this will converge. And the reason why, this is a geometric series. Right, r is negative 1/4. More importantly, we could take the absolute value of r and see that it's 1/4. And anytime we have r is less than 1, it'll converge. That series will converge. Okay. If we look at the series in the bottom, negative 5/4 to the n. If we have n is 0, first term is 1. When n is 1, we have minus 5/4. When n is 2, we have positive. That's squared, so 25/16. When n is 3, that would be a negative 125/64. And this will continue like this. So here we notice that r, absolute value of r is 5/4. And this will be greater than 1. So this will diverge. In fact, this will go out of hand, like very quickly. This will converge, and the other one will diverge. Okay, so this notion of taking the absolute value of the common ratio will come into handy when we talk about the absolute convergence test. Okay. Absolute convergence test, we take the absolute value of our formula for the series, and then if that converges, we say that the original series converges. Okay, for example here, we take the absolute value in this one, and when we take the absolute value, we get just 1/n squared. Now, 1/n squared is a p-series, right, where 2 is greater than 1. And we know that when p is greater than 1, that converges, right, that series converges. So therefore, we would say that this series converges by the absolute convergence test, and it converges absolutely. Okay, we would say it converges absolutely when the corresponding series of absolute values in that series converges. Okay, let's take a look at this next one. We have sine of n/n squared. Now when we take the absolute value, okay, that means we would have absolute value of sine sine of n. The denominator would, when it's squared, it turns positive anyway. Now, keep in mind that this is going to behave kind of like 1 over n squared, only for the reason when you take absolute value of sine n, that absolute value of sine n, well, think about sine in general. Sine fluctuates between 1 and -1, right? The sine curve fluctuates between 1 and -1. When we take absolute value of it, then we get everything between 0 and 1, basically. Okay, so this is going to be less than or equal to 1 over n squared. Okay, and we know that 1 over n squared converges, right? It's a p-series. So therefore we would say the original series, without the absolute value, the original series converges. And it converges absolutely. Okay. Let's take a look at another test. We call it the ratio test. In the ratio test, we take our formula and we find the n+1 version of the formula, and we put it as a ratio over the original formula. Take the limit, and if we get a limit, this is our Greek letter rho, looks like a P, then the series converges absolutely if rho is less than 1. The series diverges if rho is greater than 1, or rho is infinite, and the test is inconclusive if rho equals 1. Okay, so let's take a look at whether or not this series converges or diverges. Okay, so what we will do then, we will take the limit as n approaches infinity of absolute value of an plus 1 over an. Okay, so we have basically, this would be, if it's the n plus 1, this would be 2 to the n plus 1 plus 5 over 3 to the n plus 1. And then we're going to divide this by our original problem in the series. So divide by 2 to the n plus 5 over 3 to the n. Now when we divide like this, we're going to multiply by the reciprocal. Right, so we have limit as n approaches infinity, 2 to the n plus 1 plus 5 over 3 to the n plus 1 times 3 to the n over 2 to the n plus 5. Okay, so now what we could do is we could reduce this a little bit. Okay, and the way we do that, here the 3 to the n plus 1, let me just rewrite this. 3 to the n plus 1 would be 3 to the n times 3. Okay, so that allows us to cancel. We can cancel 3 to the n with 3 to the n. So now we basically have 1/3 with the 3 in the denominator here times 2 to the n plus 1 plus 5 over 2 to the n plus 5. Okay, so let's take the limit as n approaches infinity, and then let's see what happens. Okay, so we could divide everything by 2 to the n. Okay, divide this by 2 to the n, divide this by 2 to the n, divide this by 2 to the n. So that means we're left with, we have 1/3 times, now on the top here this would be 2, this will go to 0, this will go to 0, and the bottom here this will be a 1. So we would have 1/3 times 2, which will give us 2/3. Okay, so what does this mean? Because rho is less than 1, right? 2/3 is less than 1. We can say that the series converges, and it converges absolutely. We say that AN converges absolutely. Okay, any questions on this? Now I want to point out that sometimes we get the notion that 2/3 becomes the sum of the series, and that's not true. The sum of this series is not 2/3. Okay, this 2/3 only tells us that the series converges, and it converges absolutely. Okay, if we want to figure out what the series would sum to, we could do that with this because this is a geometric series. Okay, so let's take a look real quick. Okay, so I could treat this and I could split this up, and by saying I have 2 to the n over 3 to the n plus summation 5 over 3 to the n. Okay, so by having this 2 to the n over 3 to the n, this is like saying I have 2/3 to the n. And then here, the 5 I could pull outside the summation. So I have 1 over 3 to the n. Okay, so for the 2/3, keep in mind n is 0 to infinity. That's 0 to infinity. I could use my formulas for sum of a geometric series. My first term in this one will be 1. So I have 1 over 1 minus my common ratio of 2/3. And then in this one, when n is 0, I get 5 times 1. So my first term is 5 over 1 minus, and my common ratio here is 1/3. Okay, so I have 1 over 1 minus 2/3 would be 1/3. So 1 divided by 1/3 is 3. And then here, 5 over 1 minus 1/3 is 2/3. So then we have to figure out what's 5 divided by 2/3. It's like saying 5 times 3 over 2. So that's 15 over 2. And so we could combine that. 3 would become 6 over 2 plus 15 over 2. So that means our sum for the series would be 21 over 2. Okay, let's take a look at another example. Okay, we have factorials. So we have 2n factorial over n factorial n factorial. Okay, so if that's the case, let's first get our a n plus 1 term. So for the n plus 1 term, we would have 2n plus 1 factorial. And then for our denominators, we would have n plus 1 factorial, n plus 1 factorial. Okay, so we're going to do limit as n goes to infinity of an plus 1 over an. Okay, so let's do that. Now if I distribute the 2 here in the top, I have 2n plus 2. Okay, so I have 2n plus 2 factorial over n plus 1 factorial times n plus 1 factorial. I'm going to go right into multiplying by the reciprocal of the bottom. So that would give me n factorial on top and 2n factorial on the bottom. Okay, so now I could expand on my 2n plus 2 factorial, because what that means is I have 2n plus 2, and then remember factorial, you just drop one number every time you multiply the next term. So that means 2n plus 2 times 2n plus 1, and then times 2n factorial. Okay, and then we have times n factorial times n factorial. Okay, denominator, I have n plus 1 factorial so the n plus 1 factorial means I have n plus 1 times n factorial, and then for the other n plus 1 I have another n plus 1 times n factorial. Okay, and I still have the 2n factorial there. So you could cancel a lot of things now. Okay, we could cancel out the two 2n factorials. We could cancel out the n factorials. Okay, so we're left with 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. Now, once I see this, I have the 2 I could pull out of this factor. So I have 2n plus 1, and then inside I have 2n plus 1, n plus 1 times n plus 1. Okay, cancel an n plus 1 from top and bottom. So I have, if I distribute the 2 in here, I have 4n plus 2 over n plus 1. Okay, take the limit as n approaches infinity. So divide everything by n. Okay, so this goes to 0, this goes to 0. I have 4 over 1, which gives me a limit of 4. Okay, and remember what we said, this is our rho. So when rho is greater than 1, we say that the series diverges. Okay, let's take a look at another example. Okay, so let's set up our a to the n plus 1. So that would make it 4 to the n plus 1 times n plus 1 factorial n plus 1 factorial over 2n, so we gotta do 2 and then n plus 1 factorial. Okay, that's going to make that become 2n plus 2 factorial. I might as well change it to say 2n plus 2. Okay, let's go right into the ratio test. Dividing by the original series or multiplying by its reciprocal. So multiply by 2n factorial over 4 to the n factorial, n factorial. Okay, so we see really quickly that we could write 4 to the n plus 1 as 4 times 4 to the n. Okay, n plus 1 factorial would be n plus 1 times n factorial. Another one next to it, n plus 1 times n factorial. Denominator would be 2n plus 2 times 2n plus 1 times 2n factorial. Okay, times 2n factorial over 4 to the n factorial, n factorial. Okay, So canceling time, we got 2n factorial, that goes away. N factorial with an n factorial, another n factorial with another n factorial. We have a 4 to the n and a 4 to the n. They're gone. Okay, so what are we left with? We have limit n approaches infinity. We have 4 times n plus 1 times n plus 1 over 2n plus 2 times 2n plus 1. Okay, and then what we could do is in the bottom, this factor, we could pull out a 2. So we have 4n plus 1, n plus 1 over 2n plus 1, and then 2n plus 1. Cancel out the n plus 1s. You could reduce here 2 over 1. So if we distribute the 2, we get 2n plus 2 over 2n plus 1. Okay, and so as we take the limit, as n approaches infinity, we could divide everything by n. Okay, this goes to 0, this goes to 0. We end up with 2 over 2, which is equal to 1. Okay, and remember what happens when rho equals 1. We say that the test is inconclusive. So inconclusive. Now, one thing we could take a look at in general, if you look at the final limit, 2n plus 2 over 2n plus 1. Okay, so you see that the top is always bigger than the bottom. So when that happens, as the top gets bigger than the bottom, we know that this does not go to 0, right? This is going to be a ratio that's larger than 1. Okay, so what that kind of tells you is it's going to diverge. Okay, if you're looking at the nth term, this is going to end up diverging. Okay. So if we go strictly from the ratio test, we say inconclusive. But if we look at like an nth term tells us based on this is going to be top, well, they're both about the same. Very slight difference. You're just going to add an extra 1 to the top. But that would be enough to make this top heavy, and this will go to diverging in the long run. Okay, so it's important to note that. Okay, let's take a look at the root test. So in some cases, the root test can be very useful, especially if you have things raised to exponents and you want to get rid of those exponents really quickly. You would take an nth root. right? You take the nth root of the absolute value of that series, and you end up with rho. And so the rule is the series converges absolutely if rho is less than 1. It diverges if rho is greater than 1, or rho is infinite. And the test is inconclusive if rho equals 1. Okay, so let's take a look. Example 3. Consider the series with the terms an equals n over 2 to the n when n is odd, and 1 over 2 to the n when n is even. Does the series converge? Okay, so we apply the root test. Right, so if we have a, and we're going to do nth root. Okay, so that means for the top one, if we do nth root of this term, well, that would leave us with nth root of n over an nth root of 2 to the n. Let's do that. And then we'll just simplify it. And then for the bottom scenario, we will do nth root of 1 over nth root of 2 to the n. Okay, so nth root of a to the n, a sub n. So nth root of n, okay, that'll stay. And then nth root of 2 to the n, the nth root and the 2 to the n, the n's will cancel. So you'll just be left with 2. Right, the nth root with the nth power, they totally cancel. You're left with what's underneath. So 2. And then for your denominator, you're left with, well, nth root of 1. Any root of 1, you'll still have 1. Okay, so you'll have 1, and an nth root of 2 to the n will be 2. Okay, so you'll have this scenario. So you'll have basically that the nth root of an will be between these two values. Okay, so let's take a look at that real quick. Nth root of an, it'll be less than or equal to nth root of n over 2. It'll also be greater than or equal to 1/2. And then what we say is, since we have the limit of the nth root of n goes to 1, if we have the limit as n goes to infinity, of nth root of n, nth root of an, this will be equal to 1/2. Okay, and one of the things we have to remember, back in section 10.1, we had those 5 or 6 popular limits. The limit of nth root of n goes to 1. Okay, so this thing that we see here, that's going to be a 1. So based off of the sandwich theorem, we know that this is going to have a limit of 1/2. Okay, and so we have rho being 1/2, and since that's less than 1, we would say that this series converges absolutely by the root test. Okay. Let's take a look at a few more examples. Okay. Does this converge or diverge? Let's apply the root test to see what happens. Okay. So we take n squared and 2 to the n, we apply the nth root. Okay, so that gives us, for the top, we just have the nth root of n squared over, and then the nth root of 2 to the n. Now, another way we could look at the top, this would be the nth root of n squared. The bottom would be 2. And now we know from our previous example, the nth root of n, the limit as n goes to infinity, that just becomes 1. So this is 1/2. And 1/2 is less than 1, so therefore this would converge. Okay, by the root test. Let's take a look at another example. Okay, so here let's do nth root test, 2 to the n over n cubed. So nth root of 2 to the n over nth root of n cubed. Well, for the top, this will become 2, right? Nth root of 2 to the n, that's just plain 2. And on the bottom, this will be the nth root of n cubed. Now again, this nth root of n, as we have a limit as n goes to infinity, that becomes 1. So this becomes 2, which is bigger than 1, which means that this would be divergent. Right? So this diverges by the root test. Okay, and then let's take a look at our last example. We have 1 over 1 plus n to the nth power. So let's apply the nth root test. 1 over 1 plus n. Okay, so the nth root and the nth power, they will cancel. That will leave us with 1 over 1 plus n. And as we take the limit as n approaches infinity, 1 over 1 plus n, that would just go to 0. Right? Denominator would get really big, and this would become 0. 0 is less than 1. So we would say that this one converges by the root test. Okay, any questions, just write me an email. That's the end of the lesson for 10.5. Have a good day, have a good night. We'll see you soon.